Next, we're going to look at solving polynomial inequalities. Now, as we know, when we're looking at inequalities, we can be looking at when a function is less than or equal to, greater than or equal to a specific number. However, we can also compare two equations. So if you look at the functions below, we have f at x and we have g at x. I want to know which intervals display that f at x is greater than or equal to g at x. So first, let's identify where g at x is. So it's our linear function right here. So I want to know when f at x is greater than or equal to g at x. So we can identify when it's greater than, so starting here, it's greater than, up until this point, and then this part would not be included because it's less than, and then once again it's greater than starting at this point here. So how would we state those intervals? Well, we have to look at the x values for when f at x is greater than g at x. So if we look at the x values, so starting here, the x value for this one is negative 2.5. So from negative 2.5 until what point, what x value is f at x greater than or equal to our function g at x? Well, up until this point is when they're still equal to each other. So this point is 2. Now, does it include negative 2.5 and 2? Yes, it does. So we can either say when x is in between, so n including negative 2.5 to 2, or we can use interval notation. So that's set notation. If we use interval notation, because it includes those values, we would use square brackets. So from negative 2.5 to 2. If it did not include those values, so if this was just greater than, then we would use round brackets. Now, it's also going to be at this point here and greater than. So when x is, we'll say this is 4.8. So when x is 4.8, when x is 4.9, when x is 5, and any number where x is greater than or equal to 4.8. So we'd say when x is greater than or equal to 4.8. And then in terms of the interval notation, so it includes 4.8. And as you can see, it's going to be for any value that's greater than 4.8. So that would be all the way to positive infinity. And infinity does not have a bound on it, so we would use a round bracket. Okay, so when we're solving polynomial inequalities, the first thing we're going to do is simplify our equation, because if we're given two functions, we want to bring everything to one side. So we're bringing all terms to one side. Afterwards, we're going to factor to find the roots. So in other words, you're finding your x-intercepts. Next, we're going to test the values in between your roots. So we'll talk about this more in a moment. So as you can see, we are given the inequality x multiplied by x minus 4 multiplied by x plus 3 is greater than or equal to 0. So we want to know when this is true. This is already factored for us, as you can see. So we're going to decide what our roots are. Because it's already factored, we can see that the roots are when x is equal to 0, when x is equal to 4, and when x is equal to negative 3. So the next thing we're going to do, we are going to test all of the values in between these roots, because we want to see when these values will give us positive or negative. So because we have 0, 4, and negative 3, we are going to set this up in order. So we're going to start with negative 3. So we're going to check numbers where x is less than negative 3. We're going to check, well, we know at x equals negative 3, it's going to be 0. We're going to check values in between negative 3 and our next value, which is 0. We know that when x equals 0, it's a root, so it will be 0. We're going to check when x is in between 0 and 4. We know that when x is equal to 4, it's going to be 0. And then we're going to check what happens when x is greater than 4. So we're checking every side of our roots. So in order to check this, we're going to see what happens when we sub in a value that's less than negative 3 into our equation here. So when we make this chart, we're also going to include all of our equation. So we have x multiplied by x minus 4 multiplied by x plus 3, and we're going to see what that equals. So imagine a number less than negative 3, say negative 4. If I sub in negative 4 for x, what do I get? I get negative 4, which is a negative number. If I sub in negative 4 for x minus 4, what would I get? I would get negative 8, which is a negative number. And if I sub in negative 4 for negative 4 plus 3, what do I get? I still get a negative number. So as we can see, these are being multiplied by each other. So what happens when I multiply a negative by a negative? I get positive. And then if I take that positive number and I multiply it by a negative, I get negative. So my final answer, anytime x is less than negative 3, my value is going to be less than 0. It's going to be negative. We know that at our roots, we're going to get 0, so we can just plug in 0 here. Okay, so this is talking about what our y value is. So let's check the other values. So we need a number in between negative 3 and 0. We can use negative 1. Doesn't matter what you use as long as it fits the parameters. So if we use negative 1 and we sub it in for x, that's negative. Negative 1 minus 4, negative. Negative 1 plus 3, we get a positive. So what happens? Well, when we multiply these two by each other, we get a positive number. And then if we take that number and multiply it by a positive, we end up with positive. So that means for any values in between negative 3 and 0, okay, not including, because it's not the less than or equal to sign, but in between negative 3 and 0, it's going to be a positive value. So our function is going to be above the x-axis. So let's check a number between 0 and 4. We could use 1. So we would get positive. Oops. We get positive. And then we would get 1 minus 4 is negative, and then 1 plus 3 positive. So we would end up with a negative number. And finally, a number that is greater than 4, we could use 5. Once again, you could use any number as long as it fits the parameters. So if I use 5, when I sub it in for x, that's positive. 5 minus 4 is still positive. And then 5 plus 3 is still positive. So positive. So what does this chart tell us? It tells us that our function f at x is going to be greater than or equal to 0 on the following intervals. So when is it greater than or equal to 0? Well, here. So in between and then when x is greater than or equal to 4. And our question did include this sign, so let me just include it here. So if you want to see what this looks like on a graph, so our function was y equals x, x minus 4, x plus 3. So let's see when y is equal to 0. So if we look at our function here, when is our function positive? Well, it's positive in between -3 and 0, and it's positive after 4. But for these values, as you can see, these values are negative. So if we go through the whole graph, it's negative. Once we get here, it's positive, the y values. The y values are still positive until we get to 0, and then they're negative again until we reach 4, and then they're positive. Okay? So we have our final statement. F at x is greater than 0 on the interval when x is in between -3 and 0, and x is greater than or equal to 4. So this time, we're going to solve this inequality using set notation and interval notation. So the previous question, we just used set notation. This time, we're going to write our answer twice. But what do you notice? Our function is not factored, so you cannot see what the roots are right away. We need to factor it. What degree is our function in? Well, we have 2x cubed minus x squared minus 5x minus 2 is greater than or equal to 0. So what we're going to do, we're going to use the factor theorem because this is a cubic function. So we're going to use the factor theorem. We're going to use values that go into 2. So I'll give you a moment to check plus minus 1 and plus minus 2. So which value is going to make this function equal 0? So now that we know that f at 2 makes this function equal 0, we're going to divide. So we have x minus 2, and then we have 2x cubed minus x squared minus 5x minus 2. So 2x cubed, we're going to divide by x. We get 2x squared. Multiply, we get 2x cubed minus 4x squared. Subtract, we get 0, and we get 3x squared. 3x squared divided by x, we're going to get 3x. Multiply 3x by x minus 2, we get 3x squared, and then we get minus 6x. Subtract, we get 0, and we get x. Bring down the minus 2. Divide, we get plus 1, and then we multiply. And as you can see, as expected, we get a remainder of 0. So now we have 2x squared plus 3x plus 1. That's great. So we have x minus 2, and then we have 2x squared plus 3x plus 1. What do we need to do here? Well, we need to factor this further so we can get all our roots. So you're going to go ahead and use product sum. I'm not going to go through the steps for that. You can pause the video and complete the factoring. So you should get x minus 2, 2x plus 1, and x plus 1. So what are the roots then? Our roots are going to be x equals 2, x equals -1/2, and x equals -1. So the next thing we're going to do, we're going to put these into our chart. So to put these into our chart, we have to put the values in order. So first is going to be -1. So we're going to look at when x is less than -1. We know at -1, it's going to be 0. We're going to look at when x is in between -1 and -1/2. We know when x is -1/2, it's going to be 0. And then we're going to look at between -1/2 and 2. We know when x is 2, it's going to be 0. And then we're going to look at when x is greater than 2. So remember, we're going to use what we have for factoring. So we have x minus 2, 2x plus 1, and x plus 1. So choose a number less than -1, say for instance -2. If I sub it in here, negative. If I sub it in here, so 2 times -2 and then plus 1, we still get a negative, and then -2 plus 1, we get a negative. So overall, it's negative. And then if you choose a number between -1 and -1/2, sub in your values, and you should get a positive. You can choose a number in between -1/2 and 2, for instance 0. You should get negative. And then a number greater than 2, so for example you could use the number 4, and you should get positive. So remember, the question is asking when is it greater than or equal to 0. So therefore, f at x is greater than or equal to 0 on the interval. So we're going to use set notation first, and then we're going to use interval notation. So for set notation, it's positive here, and it's positive here. So we would say between -1 and -1/2, and when x is greater than or equal to 2. Now in terms of interval notation, so between -1 and -1/2, and it includes those numbers, so square brackets. And when x is greater than or equal to 2, all the way to infinity. So use a round bracket. So there you can see we've solved the question, and then we know how to represent our answer using set notation as well as interval notation. Now we're going to try one more. This time, I'm giving you two functions. I'm giving you f at x is equal to 3x cubed minus 3x squared minus 2x, and g at x is equal to 2x cubed minus x squared plus x. So I want to know, when is f at x greater than g at x? So we're trying to see which x values will f at x on our graph be greater than g at x. So because we have two functions here, we're not checking when it's greater than or equal to 0. We have two functions. What we're going to do, we're going to simplify our equation. So what we have to do here, we're trying to find when f at x is greater than g at x. So we'll state 3x cubed minus 3x squared minus 2x. We're trying to see when it's greater than 2x cubed minus x squared plus x. And then we're going to simplify, so we're going to move everything to one side. So minus 2x cubed plus x squared minus x. So we're left with greater than 0. And then when we simplify, we're going to be left with x cubed minus 2x squared minus 3x is greater than 0. So this is what we are going to factor. So we're going to factor x cubed minus 2x squared minus 3x. Notice there's no coefficient at the end, so we can actually factor out x. So if I factor out x, it makes it much easier to factor. So we'll have x squared minus 2x minus 3. And then we can factor this using product sum. So we have x, and then x minus 3, x plus 1. So my roots are x equals 0, x equals positive 3, and x equals negative 1. So we're going to make our chart. So remember, our chart has to be in order. So we have x minus 3, x plus 1. What does it equal? And then we have, so our lowest number is negative 1, so we're going to check when x is less than negative 1. I'm not going to write negative 1 because you understand now at the roots it's going to be equal to 0. So we're going to check when x is less than negative 1. We're going to check when x is in between negative 1 and 0. We're going to check when x is in between 0 and 3. And we're going to check when x is greater than 3. So you choose whatever values you want. So if we use, say, negative 2, we get negative, 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 so our answer is negative. We use a number in between negative 1 and 0, so that could be negative 0.5. And you get negative, negative, positive. A number between 0 and 3, you could use 1. You get positive, negative, positive, so you end up with negative. And finally, a number greater than 3, you could use 4, so you'd get positive, positive, positive. So this is going to help us with answering our question because we're asked when is it greater than, so when would it be positive? So we would state that, therefore, f at x is greater than g at x on the interval. So there's no specification here of what to use. You could just use set notation. So in between negative 1 and 0, and when x is greater than 3. So let's actually verify this. So we have our function 3x cubed minus 3x squared minus 2x. And then we have 2x cubed minus x squared plus x. So our f at x, that's the purple function. And then our g at x is the black. So you want to see when is this purple function greater than the black. So between negative 1 all the way until 0, that's when it's greater than. And then when would it be greater than again? As you can see at this point here, it's now greater than once again. So our math is correct. So we're just checking the interval when the specific function is greater than or equal to, less than or equal to.